Okay, we should now have sound now. I don't know why my audio had cycled off. So in today's lecture, like I was saying to the in-person class, what we're going to do today is use the top-down stepwise refinement along with method decomposition to build that game of craps we talked about prior when we were still in the downstairs lab and had some technical difficulties. And so the purpose of this is so that we can get everything uploaded onto YouTube by the end of today to where we're currently at, which is past arrays. And so this will be a good time to go ahead and reflect back on some of the concepts that relate to methods. So here in today's lecture, we'll talk a little bit more about magic numbers versus named constants. We'll talk about local variables versus class variables versus instance variables. Instance variables will be the interesting thing to learn about today, because that's where we're actually going to be moving after today's lecture is done, starting in the next lecture, when we start talking about objects and being able to create our own objects. We'll get a little tasting of that in some sample code here. We'll talk about the enumerated types as custom data types that we ourselves can define, and they're most comparable to the way that the primitive data types are. We'll talk more about that when we get to the slides. When we talk about enumerated types, I want to illustrate how powerful they are to match with switch statements. So probably the case of using switch statements will be to empower your ability to use enumerated types. So they pair off very well. We'll also talk about the method activation stack. So when we go ahead and invoke a method and then another method invokes another method, what is the order of execution on there? And then finally, we're going to build our game of craps. Perfect. Okay, so here, just a quick example of what we should always strive for is there's the concept of magic numbers. Magic numbers is simply a number that is embedded into your source code as a part of the logic. So typically you have a computation, or you have a selection, or you might have a repetition structure that relies on a hard-coded value. And as software engineers, you want to avoid this. Real engineers will see love magic numbers. Mathematicians do too. But in my opinion, both mathematicians and engineers don't name things well. And so one thing that we're going to really strive to do from the get-go when we're talking about self-documenting code is that we want it to be as readable as possible. And so even if you have a value that never changes, instead of just hard coding that value, it makes more sense to give that value a name, a human readable name, a name that provides context to that number, and then apply the final keyword so that it's not mutable, so that it's not writable, so that it's only readable, because you want, if it's not supposed to change, don't allow it to change, but it also makes your code much more readable. So for the example in this slide, we were computing the area, and if we just hard-coded the values, it is true we could get the area we are looking for. In the example in the slide, it's 3.14159 times 3.15 times 3.15. Now, with the way that it's illustrated, those are all what we would call magic numbers, and then you have to apply context to understand what's happening. So you probably look at the 3.14159 and you say to yourself, well, that looks like it's probably an approximation for pi. And in this instance, you'd be right. But you had to make that assumption yourself. Then when you look at the next number, 3.15 times 3.15, that's not obvious at all. And actually what it's meaning to convey is that that was a radius value, right? So clearly the area being computed there is pi times radius, right? Which is the area of a circle. But again, notice the second block of code is much more readable than this first block of code, even though it's 4 times longer. So that's the thing. Sometimes readability comes at the cost of verbosity. It's more verbose, but that's all right. It's better to be readable and understandable than to be brief and to be difficult to parse and understand. Okay, we talked already about the advantages of magic numbers. versus what we will now call named constants. Named constants is just a variable that we've named, but it's no longer a variable if we apply the final keyword, because now it's not writable. So once we convert a variable to be read-only, we now call it a constant. Okay, the other big thing that I think is definitely worth mentioning is to articulate the distinction between local variables versus class variables versus instance variables. There are actually 3 classes of variables that exist. So let's start with local variables. Even though that appears at the bottom, that's the first type of variable we actually learned how to use. A local variable is one that is defined inside of a code block that is in a method that is defined inside of the method. So all local variables exist within methods, but they're localized to the most inner set of curly braces that they're defined in. So the very broadest scope of a local variable is going to be inside of the method itself. But it's possible in the method where you create a selection statement, like an if statement or a while statement that has its own set of curly braces. And if you define a local variable inside that scope, it only exists in that scope. Okay, so we all know about the scope on local variables. And if you try to access a local variable outside that scope, you're going to get an error. It's going to say symbol not found. And of course, you can't access a variable before you declared it. So always the rule for every variable in Java is you have to declare it before you can use it. And once it's been declared, you can only use it for so long as it's in that scope. So moving on from local variables, the next type of variable that we learned about were class variables. These are the ones that are defined inside of the class scope alongside our methods. Now, we apply the ones that are called class variables. We require the use of a static keyword to be applied to it, just like what we've seen with the main method. And so what that allows us to do is access that variable or field. Another name for a variable in Java is a field. One way to access that field is using the class name. Now, there's one other variable, and we're going to get into that later this week. It's called an instance variable. It, like the class variable, is defined at the class scope, but it does not use the static keyword. And by not using the static keyword, it's no longer a property of the class itself, but a property of an instance of the class, which means that it can have an individual value for every particular instance of the class we create. So I'm not going to get too deep into that this lecture. We're going to learn much more about that next lecture. Okay, so some example code of what we're talking about here. Let's take a look at this class. So this class is called variable example. I have 2 variables that are defined inside of the class scope. One of them is an instance variable. The other is a class variable. So you can see how they distinguish from one another. So the only difference is that the class variable uses that static keyword, whereas the instance variable does not. Okay, let's make a main method. So inside of our main method here, I will then create a local variable. So this is my local variable here because it's defined inside of a method. And if I wanted to print out the state, it would print out right here. And then I can also access my static variable by just using the name. Now, recall, I can only just use its name so long as there's no other name inside this method. So as long as there's not a shared name, it defaults to looking at the class scope. An alternative way and a safer way of accessing the static variable is to use its full qualified path. So the path to this variable is scoped inside of the variable example class. So I could use the class name, then I could use the dot operator, and from the dot operator, I can then access the variable name. And then finally, the instance variable. Now, typically, this is a faux pas. Typically, on instance variables, we don't assign them a value in the class scope, but we can. And for the purposes of this demo, I'm going to show you this. we are going to assign instance variable here to our instance variable, but to access it, the only way it gets constructed is when we call to create a new instance of our variable example class. You've seen the new keyword before. Effectively, what you were doing every time you invoke the new keyword is it creates all the instance variables. So these instance variables don't actually exist until you use the new keyword on top of that class. And then any instance variables that are declared within that class are then created. So they don't exist until this new keyword has been applied to it. And then only for this instance. So the moment that this falls out of scope, that variable no longer exists. Okay, is there any questions regarding this? And again, we can prove that this works. We can take this code and, oh, we already have it pasted here. So variable example. Okay, let's compile, and this might need to blow up some for the class. And let's run that. And here you could see this is the local variable. This is the static variable. This is also the static variable. And this is going to be the value of the instance variable, which we actually got to print out. Okay, the next thing I want to talk about is the enumerated types. So enum is a very powerful component that's given to us. It's a top level keyword that goes at the same level that a class goes to. So there's one of three keywords we can use to declare our Java source code files. They can either be class, which we've kind of used, but we haven't really talked deeply about. We'll talk deeply about that later in the week. There's interface, which we'll talk about at the tail end of this semester, and there's enum. So an enum is effectively allows us to create our own data type. So we learned about the primitive data types first. We learned about floats, we learned about doubles, we learned about ints and cars and or chars or Boolean values, right? And so what defines a primitive data type, if you recall, is that it's a closed set of values. And because it's a closed set of values, every possible value within that scope is well defined. It's known inside of the JVM. The thing that distinguishes a string from the other primitive data types is that there's no closed set of strings, because the number of permutations just using the letter A is infinite. Okay, so with that said, what enum allows us to do is to build effectively something that's very similar to our own primitive data type, where we can create what's called an enumerated set. An enumerated set is just one that is countable, right? There's a countable number of Boolean values. There's a countable number of integers that starts at some min value and goes to some max value. There's a countable number of characters. So here with enum, we can create our own enumerated data type that has a well-defined collection of values. And so the simplified form by which we do that is we use the enum keyword, and then we give whatever the name of the new data type we want to create is going to be called. And then we can create a set of curly braces. And inside that set of curly braces, we would have a comma separated list of all the actual values that make up our data set. And so this allows us a very powerful mechanism to start building out types that are akin to the primitive data types. So we could think of it as our own special custom data type that allows us to define predefined constants or literal values. So since these are literal values, we usually name all of the enumerated types inside of them using uppercase letters. So that's another naming convention. I hadn't mentioned it a couple slides ago, but if we jump back just to the example that we saw here with magic numbers, when I apply the final keyword that makes it a constant, all constants should be in all uppercase to highlight the fact that it's read-only and it's not writable just by looking at it. It gives us context. Okay, so some examples on when we might want to select to use enumerated types when we're building out our own software is if we wanted to give something like compass directions. Because when we think of a compass direction, we think of north, south, east, and west, right? That's a closed set of values that only makes sense on a compass, or days of the week, for instance. It's a enumerated descriptive thing. Same with the months of the year, or say, for instance, the states in the United States, or the parishes in Louisiana, or the districts in New Orleans. Like all these could be represented as their own special data type of enumerated things. So what this looks like in practice, the way we'd actually do this in action is we would create a Java file. The name of the file would be whatever our data type is. So suppose we wanted to make an enumerated data type in enum that was called day. So we would use public so that we could use it in outer classes. We'd use the keyword enum to highlight that's what we're creating. And then we give this data type a name. And so since technically it's a reference type, it behaves like a primitive data type, but it's not in the fact that it's a closed set of values. It's still a reference type. We're going to use the same rules to define other classes. So the same way that we define classes, and we'll do the same with interfaces, is we always start with an uppercase letter. So here, this is a day, and then we will give it scope, and inside the scope will be our set of values. And since these values are constants, right, they're not mutable, we use all uppercase and we distinguish them with commas. We do a comma separated list on that. Okay, so in action, this would be how we might actually implement a piece of code that then uses that day enum type. So here I have a public class main method. I have a public class main class. Inside of my main class, I have a main method. Inside my main method, I can go ahead and I can declare a variable that can now hold an instance of our own special custom enum data type. So day, let's call this day, not days. This is called, yeah, should be, okay. So here I have a variable, a data type of day, and then the identifier I give it today, then I can assign to it a value from that enum type. And to access those values, we use that dot operator. So the data type is day, and then one of the values was Friday, which is in all uppercase because that's how it's defined. And then if I were to print that out, it would print out Friday. So one alternate thing that's worth mentioning here is that enumerated types, like I said earlier, work really, really well with switch statements. So let's take a quick example of that. And when we look at an example of this, I want to highlight that even though we can create our enum types inside of its own class, inside its own Java file, we can also declare them into the scope of another class. In fact, you can do this with other class definitions as well. Like this is true for all top level keywords in Java, but it's pretty common in enum with the enum data type, with the enum type. So here I'll have a public class enum switch as my class. So since this is a class, it can now have a main method. Inside of my class, though, at the class scope, I'm going to declare a enum data type called month. And inside of month, I'm going to then use a set of curly braces to define all of the values that a month data type can contain, which is going to be January, February, March, April, May, June, July, August, September, October, November, December. Okay, so in my main method, as we stated earlier, I can now create an instance. I can now create a variable of data type month, and then give it whatever label I want to give it. I'll call it date. And then I'm going to assign to it a value from that closed set of values. So inside of month was the value January. Now, suppose we wanted to apply logic. Suppose we wanted to go ahead and determine, is a given month a part of which season? Well, we can usually split the months, right? There's 4 seasons, right? There's winter, there's fall, there's summer, and there's spring. And so winter is December, January, and February, right? And spring is March, April, and May, right? Which means that summer is June, July, and August, which means that technically we're still in fall, right? That's September, October, and November. So if it's one of those groupings, then we could say what the season is. This is a perfect time to use a switch statement. So one of the nice things about switch statements is that if we pass in date here, and so date is the data type month, then the switch statement already knows that we're switching on a month enum type, and therefore we can just use the value to define our cases and not have to use the dot operator. So that makes it much more readable, in my opinion. So since we're switching on our date, then on the case, and remember, we can define our cases in the switch statement as comma separated lists. So on the case that the value is December, comma January, comma February. So if it's any one of those 3 things, then I'll use the arrow operator, and then I'll perform this execution. I will print out that it's winter. And the nice thing about the arrow operation is we don't have to do a break statement. So if it is that thing, then it executes and then just falls down to the bottom. It's done processing. Because remember, this is an alternate form of a multi-selection statement. Okay, otherwise, if it's March, April, or May, then we'll print out spring. If the case is June, July, or August, then we'll print out summer. And then finally, if it's September, October, or November, we'll print out fall. And so this is where switch statements really gain a lot of value, in my opinion, is when you couple them with enum types. Does anyone have any questions regarding this? Does this make sense to everybody?
Why does it switch date? And can we compare above it with month date?
Yeah, so I think the question here is, we have inside the switch statement, we're passing in the date. And above it, we're actually creating an assignment of date. So one thing that's mandatory for a switch statement is that you pass in a value of something that you have. And I could have passed in a literal value. So I could have passed in, I'm going to cut and copy here. I could have passed in this, right? A realization of a literal value, and then it does comparison. So what the switch statement is doing is it's doing equality operations. Is the thing that was passed to me here, which is month.January, is it the case that happens in the first part of cases? Is it December, January, February? In this instance, it would be. But let's say it wasn't. Let's say then it would go to the next case. Is it a March, April, May? Is it June, July, August? Is it September, October, November? It might even be something, it might be an instance where you have a hole in the switch statement where it doesn't cover that case at all, in which case none of the cases would execute. So with this switch statement, it'll only execute the corresponding code that matches the case to what got passed in. And so we could pass a literal value. What's typically more powerful is that we pass in a variable, because a variable can be mutable. A variable can be processed into something different over the lifetime of your software, and then the result from your switch statement can change depending on what the state of your variable is. Does that answer your question?
Yeah, so we basically chose one.
That's right. So we arbitrarily chose one for the purpose of this code to work just as a demo. Now, in the instance of, and in fact, when we go to build out our game of craps, we're going to use obviously an enum type. That's one reason why I'm spending so much time just explaining it. And maybe that'll give more sense in how the enum type can change state, or the variable that holds the enum can change state over time. So imagine if I did this instead. Imagine if I had a user prompt that said, what month is it? And then I use that to extract the enum type that we want instead of hard coding it. So I just hard coded it here. And then if I ran this code, it could be different depending on what the user typed in for what month it is. Does that make sense? But on some of these demo codes, I tried to abstract away everything that's not critical just to highlight. And then we go back and do a real example. And I think the real example of craps should put this in perspective some. Now, another thing I should highlight with switch statements is if it's a single line of code we're executing, it doesn't need to go in, it doesn't have to be put into a code block. But probably what's better is if we did code blocks. And code blocks, if you recall, is just to put everything inside of curly braces like that. So this would actually be a better configuration of what I'm doing by blocking my code together. So I guess that would have to go there. Just like that. Okay, let's talk about the method activation stack as well, because this is an important concept. So the idea behind the way that methods work is that the JVM manages what's called the method activation stack. So a stack is a certain type of data structure behavior that works the same way you probably expect it to work. Actually, there's two different types of ways that that data structures can be kind of accessed. So if you have a sequence of values and you have to take one value from that sequence, there's three ways you can do it. You can either randomly select something from the sequence. That's what's called random access, right? You could always pick the first thing that's at the list. So the first thing, so you keep it ordered in insertions. So think of it as a line at the grocery store or at a fast food restaurant, where the first person in goes to the counter and the person after them goes after that person, and the next person goes after the person who's currently last in line. And the person that gets serviced first is the one that was first in line, right? That's what's called a queue. That's what we call lines are called queues in the UK, right? In Britain, that's the more accurate term. That's like the data structure term. That's the computer sciencey term that we use for that kind of operation, that kind of concept. So traditionally, what we call lines or queues, the alternate approach is what's called a stack. A stack is the last thing into that collection is the first thing that comes out, right? Or another way of saying that is the first thing that goes into it ends up being the last thing that comes out. Can you think of the concept of a stack in real life? You probably, for instance, are familiar with stacks with pancakes, for instance. When you make your pancakes, you probably put the first one onto the plate, and then you put the next one, the second one you make, and then the third and the fourth. When you go to eat pancakes or serve them, someone's probably taking the one that's off the very top, and then the one after that, and then the one after that. So a very natural way of thinking what a stack is would be exactly what it's named after. Things that form in stacks, where you build the stack by putting one thing on top of the other, but then you take off the stack by taking the top until you get to the bottom, which is the exact opposite of a queue. Okay, so because of that, there's two different words that are worth using. If it's a queue-like structure, we call that FIFO, first in, first out. If it's a stack-like structure, we call it LIFO, last in, first out. If you ever see those terms, that's what it's referring to. Okay, so with that said, the way that our methods are executed is based off of the concept of stacks. So we've always said up to this point that the main method is our critical method. That's the starting point of our application. The reason why that is that when we invoke the JVM to start executing code, what it does is it looks for the main method and it puts that onto the method activation stack. And then it looks at all of the lines of code, it looks at all of the statements defined in the method, and it'll execute them line by line, right? Statement by statement. So it goes to the top of that method, and then it starts executing them in order. Now, the moment that there is a method invocation as one of those statements, what the JVM does is it pauses where it's at, currently executing the method you're in, and then it pops the new block of instructions from the method that you're trying to invoke onto the activation stack. And since this concept is you always service the last thing that was into the stack, it'll then jump the instruction pointer to the new method and start executing those statements in there. And let's say, for argument's sake, one of the statements inside of this new method invoked another method. The activation pointer would that's executing all the instructions would stop where it's currently at and pop the new method on top of the activation stack. And then it would start with that other method. And then it'll eventually get to the point where it can execute all the instructions in the topmost method that's been called. Then when it's done, it jumps back to the prior one, completes those calls, and then when it's done that, it jumps back to the main method and executes those calls. And so when we refer to a method activation stack, that's what we're referring to. And in fact, we have some sample code we can look at that kind of highlights this concept. So suppose, for instance, that we had our main method where we just created a variable that's called main. And then we have a method one here. So inside of our instructions, when we go to execute this, we know that the main method is going to be the first thing that starts executing. This first statement's going to then execute. But then this is a method call. Now, message has meaning because it was set in the instruction before, and it's actually going to get passed to the next method. So we're going to stop what we're doing here. We're going to jump to method one, and it's provided some data here, which is this string. So we're going to add to that string a new string. We're going to concatenate with method one, and then we're going to pass that to method two. So we're going to stop doing what we're doing inside method one, and we're going to jump to method two, but with the string given to us from method one. So then we're going to take that string that we got from method one, we're going to concatenate method two into it, and then we're going to pass that to method three. So we're going to stop what we're doing method two, and we're going to jump to method three. In method three, we're going to grab the string we got from method two, which got that string from method one, which got that string from main, and we're going to concat on that method three. And we're going to save that as output, and then we're going to return that back to what called method three. Well, what called method three was method two. So we're going to get that return value here, and we're going to concatenate that to our output. And then we're going to send that back to the method that called method two. That was method one. So method one will then get output and concatenate onto output this new string that says method one. We're going to return this back to the thing that called method one, and that was the main method, which was line number two, where we'll finally get that output string, which passed from main to method one, to method two, to method three, back to method two, back to method one, finally back to main. And then we'll go ahead, concatenate that this is main, and finally print that out. And in fact, if we look at this, it should show that sequence of like building up and coming back down. What did I call this? This was called method activation stack. Oh, no. Stop that. Go away, IntelliJ. Don't open. Okay. So we will save this after walking this, and just to see what the output is, let's go ahead and compile and run. And we can see from main to method 1 to method 2 to method 3 to method 2 to method 1 to main. So we're putting things onto the stack, and then we take them back off. Okay. We've built up enough base knowledge of concepts to now start talking about how might we go about designing the game of craps. So when we go to build this, we want to take advantage of a couple of things. We want to use name constants instead of magic numbers. We want to use enum types to track game status. We want to use top-down stepwise refinement to define our algorithm. And we want to use functional decomposition so that we build our application split across methods. So these are all the techniques for software development that we've talked about, for software design that we've talked about, and we want to actually see them in action. We actually want to see them put to use to build a relatively basic game. So before we can start building this game, we want to talk a little bit about what the rules are of. So just as a reminder to anyone who hasn't played the game of craps, we spent a long time, I know, talking about stochastic processes and the different distributions of random numbers, the difference between uniform versus Gaussian or normal. So in the game of craps, we roll 2 die. So we know from our prior discussions that rolling 2 die is a Gaussian or normal stochastic behavior. So it's going to exhibit something that looks like a bell curve, where you're most likely to roll something that's a 7. And then after that, it's either going to be a 6 or an 8. Then after that, it's going to be the 5 or the 9. And it keeps going all the way until it's just a 2 or a 12, right? Okay, we roll 2 die. Now, if you roll a 7 or 11, then you win on the first round. And if you roll a 2, a 3, or 12 on the first round, then you lose. So there's certain values that if they occur, you win. And if they occur, you lose. And if they don't occur, then you neither win or lose on the first round, but you have to remember what you rolled, and then you progress to a new round. So in the next round, you roll again. If you roll a 7, then you lose. If you rolled the same thing you rolled on the first round, then you win. And you keep continue to play until you either win or lose. So that's the basic game of the game of craps. Does anyone have any questions about that? Does everyone kind of understand the rules? Okay, perfect. So let's start using the top-down stepwise refinement process to actually articulate how we might develop that set of rules into a software application. So the first thing we always start with is our top statement. Our top statement is a very brief elevator pitch way of describing what it is that we're building. So here, my top statement will just be the game of craps. So it abstracts a lot of things away. And recall from the top-down stepwise refinement process that we should always use our top statement as the header comment inside of our Java file. So then the next thing we're going to do is we're going to move on to the next refinement. We're going to, now that we've defined what it is we're building, we're going to think initially, what are the core, critical, abstract things we even have to think about? And this is usually broken down into 2 things. The first is our data model. What are the things that we're using? And then the second of all is going to be the basic sequence of events that have to happen for this code to work in order to get our whatever it is we're modeling, whatever behavior we're trying to automate to actually execute. So inside of refinement 1, I'm going to say, I got to set up my data or my data model, right? Always. Every algorithm is contingent to and built on top of that. Then after that, we play the first round, because that's what we talked about. Then we would report the game results, because you could either win or lose after the first round, or you might have to continue. And then if there is no winner or loser, you move on to the next round and you continue while there's no winner or loser, whether you won or while you haven't won or lost, you continue playing the game. And when you have finally either won or lost, then you print your final results. Then you print the game results and report what the final condition is. Okay. Does anyone have any questions with refinement 1? Did that kind of capture the general essence about what the game of craps is about? Any questions? Have I gotten to a point where you feel like you could have done this yourself yet? Okay. So then the next thing is we would examine refinement 1 and we ask ourselves, is this enough information for me to start encoding this as a Java file? And the answer is no, right? These are too abstract still for me to do a line-by-line translation from the English statement into a Java instruction. So then I would go through and do another refinement step. So the second refinement might look something like this. I'm going to set up my data. So what I'm effectively doing, and I should also state, recall when we're talking about this, the first refinement, after we define our first refinement, that is usually what's going to be the makeup of our main method. So the first top statement is usually the header comment in our Java file, and the main method is usually supposed to be devoid of minutia, of all the little details. It's supposed to be a broad view of your algorithm at large that is super readable. Usually just an invocation of method calls that they themselves are super readable. So keep in mind what refinement 1 says, because chances are when we go to implement this, that's exactly going to be what our main method's going to look like. Okay, so what I do in the next refinement, recall, is I go on a line-by-line basis from my refinement 1 step, and I break it down into the individual lines that have to happen. So let's say, and this process is what we call functional decomposition, where we start looking at these concepts that aren't so well defined that you can translate directly into Java, because it takes multiple actions, it takes multiple instructions to do, but we encapsulate those instructions by whatever we call them in refinement 1. We're breaking apart the logic that we've defined, that is all the logic that our software needs, into what can be smaller bite-sized function calls. Okay, so with that said, in refinement 2, I'm going to take this first line that says setup data, and I'm going to say, okay, this is the setup data line. This is the things, this is the data that my data model needs in order to do this. I'm going to have to track a game status, right? That game status lets me know whether I've won, or have I lost, or must I continue, right? Those are the 3 states that this game maintains. Okay, what are other data that we might need to know, that we might need to have access to play the game? The my point. The my point represents if you didn't win and if you didn't lose, then you have to remember what it was you rolled on the first round, because you got to replicate it. You got to reproduce it, hopefully in some new round. So if that's the case, we're going to have to store that. We're going to have to remember that. We're going to have to give it a name. So we'll have my point. And then finally, we have all of the special magical numbers, the special values that indicate whether we've won or lost. The special values, the named values that control our logic that we make decisions on in the game of craps is 7, it's 11, it's 2, it's 3, and it's 12, I believe. Okay, so after we've declared this amount here, we can say, okay, we're done defining all of the data. Let's move on to the second statement and better define what has to go there. So it's play the first round. What do we have to do to play the first round? So I'm going to create inside of my document the first round, because that's the second line. And then inside of there, I'm going to start breaking down the logic. Well, to play the first round, I'm going to have to roll some dice. I'm going to roll 2 dice. I'm going to roll 2 dice on a roll of 7 or yo. So yo is a specific term for dice rolling to mean what value? That's right. It's 11. So notice 7 is going to be in all uppercase letters because that's what it's actually called when rolling die, but we should use what it's called and not just the number. Same with 11. 11 is the value, but the name of it in the context of rolling dice is yo. Okay, then we would update our game status to say, hey, we won. On a roll of snake eyes, what value is snake eyes? 2. Yeah, it's 2 ones. So again, we have the value 2, but it's got a name in the context of rolling die, and that's snake eyes. What about tray? 3, right? And finally, boxcars. 12, exactly. So notice, because these values are special in the game of craps, then they should be special in our code. Okay, so if it was any one of those values, then we would update our game status to lose. And then finally, if it's any other roll, then we would go ahead and remember my point. Oh, now for next round, so now here, I would say, okay, now we got to print the game results. Well, game results is here. This is kind of blocking my way here. Okay, so for my game results, I'm doing that twice. So I'm only going to encode it once, right? I have it here and here. So I'm going to have print results. I'm going to say on the results, if my game status is win, then I'll print a victory message. If my game status is lose, then I'll print a loser message. And if my game status is continue, then I'm going to print a continue message. That seems easy enough. And then finally, I will go ahead and take a look at, well, while there is no winner or loser, then we'll continue to play the next rounds. So what's a next round look like? For next round, we roll 2 dice. And on the roll of player points, we update our game status to state that we won. Otherwise, if we rolled a 7, we would update our game status to lost. And if we didn't roll my point, and if we didn't roll 7, then we've neither won or lost. We've moved to the next round of the game. Excellent. So at this stage, I would look at my refinement. I've now performed a functional decomposition off of my refinement 1. And I can say to myself, I think each one of these subcategories is defined well enough for me to start encoding this, for me to start implementing this as a Java file. So at this time, I am done with the design work as text, as pseudocode, and I can move to start implementing this as a set of instructions. So the first thing I would do is I would define my enumerated type to track the game status. Notice inside of my pseudocode, I was tracking 3 different states on my game status. I could have either won the game, I could have either lost the game, or I can be in a continue state where I haven't yet won or I haven't yet lost, and my logic is based off of that. So it makes sense to me then to now define a enum type that we could call status that has 3 values: continue, win, and lose. Now, it's true, I could implement this in a much clunkier way by using 2 Boolean values. I could create, like on the bottom here, I could create an is game over Boolean that is either true or false, and a is winner that's true or false, because that captures the 3 conditions of whether I should continue the game or not continue the game. And if the game is over, then am I in the winner state or am I in the loser state? So I could do that, but does everyone see that this is more verbose? This is clunkier. This makes us track more variables. This is a less elegant approach. So even though it's possible to do it with just Boolean, we should use the more expressive but more powerful enum construct so that we can get really the control, the granularity, the implementation that we envision in our pseudocode. Okay, so let's go ahead and actually create this. So I'm going to create a status.java file. And inside of this status.java file, it's down here. Wait. It's down here. Okay. Inside of here, we're going to create our enum that's status that has the 3 states: continue, win, lose. We will save that. And we'll even double check, make sure there's no syntactical errors. Every time you create a new change, you should always try to compile it just to ensure that you don't have any typos. Because one of the worst things that you can do, and I see this a lot with the labs, is that people will go through and they'll keep building complex levels of code without ever testing it. And then what happens is when you do go to test it, you either get like 100 errors or you get erroneous behavior. And then it becomes very challenging to know where in the code base it went wrong. If you make small changes in a test and you're happy with the changes, then when something finally does break down, you know exactly where in your code to go check to see what's causing the breakdown to occur. So testing is super important. Get into the habit of doing that. Okay. So the next thing we're going to do as we implement our game of craps is we're going to take my top statement and we're going to rebrand it. Instead of top isn't very descriptive for anyone else. We'll use something like description. The game of craps. And then we'll put name, Ted Holmberg. Always give yourself credit for what you write. You probably do it when you write stories, novels, research papers. Do the same for source code because it provides you as the responsible entity for questions related to it, for citations related to it. Okay, so the first thing I'm going to do is I'm going to use that top description as my header comment. I'm going to include my name, and then I'm going to do public class craps. So the next thing I'm going to do is, and let's, okay, the next thing I'm going to do is inside of the craps class, I'm going to take some of those comments from my document. So remember, I have the setup data line that says I had to go ahead and have my constants used for, in fact, let me actually grab that here. I should use the actual one. So let's see. So here. I want to use this. These comments, and let's change that color to whatever it is, green. Perfect. There we go. So I'm going to define, so I'll go ahead and put my data model that I have commented out here because that's going to guide my implementation. Then I'm going to create a main method, and inside of my main method, I'm going to comment out my refinement 1. Remember, I said pay special attention to refinement 1 because most often is the case that should represent line by line the set of method calls we're going to perform to actually execute your algorithm as a whole. So I'm going to play the first game. I'm going to print the game results. While there is no winner or loser, then we'll continue playing the next rounds, and then we'll print the game result. Then in refinement 2, I broke each of those lines down and I defined kind of a sub pseudocode for each of those things. Well, I'm going to create a method that represents each of those actions. So I'm going to create a method that's called first round. I'm going to create a method that's called next round, and I'm going to create a method that's called print results. And for this particular purpose, notice that first round does have a return type. After the first round, we're going to get back a status on our game. Did we win the game? Did we lose the game? Or did we continue the game? For the next round, there's going to be a status that we should get back. Did I win? Did I lose? Or did I continue? For printing, that's just reporting to the user. We don't need to get any information back. We're just going to display. So that's going to be return type void. So here, what I'm doing is I'm defining what methods is this application going to require, and I'm going to stub them out. Stub them out means that I leave them empty. I've declared them, but I haven't implemented any of the source code yet. I haven't implemented any of the instructions, but what I have done is make some pretty critical choices as to what type of data do I have to pass in and what kind of data do I expect to get back out. And in fact, I think, okay. So once these choices have been made, that's where we're at. So once these choices have been made, where I have comments that represent my data model, I have comments that represent my main method, I have stubbed out empty versions of my methods, I'm now going to go and take the code descriptions from my refinement 2 of the top-down stepwise refinement, and I'm going to paste those into the curly braces, into the body of those methods, because that tells me what each of those methods do. So again, this is going to it's going to act as a guide. It's going to guide me on how to implement each of these individual methods. I did all the brain work during the pseudocode stage. I want to take advantage of that. So I'm going to just cut and paste it in and use that as my code comments. So here I have the first round. Here, this is what we already read for the next round. And here, this is what we had already read for the game status, for printing the game status. So now it's time to start coding. So inside of our states, we have the constant values that are going to be used to represent our game rules. So we're going to make those class scope, so we have access to them in all of the methods defined in our scope. We're going to make it private to the class, because the only class that needs to have access to our magic numbers, to these roles, is inside of our craps game. So we're going to use an access level of private. We're going to use static because we might need access across multiple methods. We're going to use final because these aren't supposed to be writable. They're only supposed to be readable. They're representative of actual values that occur in the game of craps. They can be represented as integer data types. A roll of 2d6 could be very easily represented as an int of either 2, 3, 4, all the way up to 12. Here for Snake Eyes, since this is immutable, since this is a constant value, we're going to use all uppercase. So here I'll have Snake Eye set to 2, Trey set to 3, 7 set to 7, Yo set to 11, and Boxcar set to 12. I'll also go ahead and will define my player point. My player point will also be something that might potentially have to be accessed across multiple classes. It might get set in the first round. I'm sorry, in multiple methods. It might get set in the first round, and it might have to be used in the other rounds. So here I will go ahead and create a static variable to represent my point. And so then the next thing I'm going to do is I will then, after declaring the data model that exists inside my class, I can now start implementing all of the methods. And I'm going to start with the main method. So my main method, I could probably build out entirely like this. Once I create my main method, and since I've stubbed out my method names already, I will never have to mutate it again. So what is my main method? Well, to the left, to the right is the original pseudocode instruction we have, and to the left is the Java instruction we can use to represent that. So when we said we have to play the first game, well, what is it to play the first game? It's to invoke the first round. Play the first round. How do we play the first round? We invoke the first round method. And remember, that's going to give us back a game status value. So we'll get back the game status value, and we will save that into a variable of data type status. So then what do we do for the next instruction, our main method? Well, it was to print the game results. What might that look like? Well, that's going to be an invocation to our print results method that we've already declared. It doesn't have a Java implementation yet, but it has a pseudocode implementation. So here, we'll pass the game status to our print results. Remember, what the pseudocode implementation was that if our game status was to win, then we would print a win message. If it was lose, we'd print a lose message. If it was continue, we'd print some kind of continue message. Then we said, so long, so while you don't have a winner or loser, we continue to play a next round. Well, how can we represent that? We can use a while statement, and we check the game status. Is the game status equal to continue? So long as it equals continue, which means it's not win or lose, then we will play a next round, which will give us back a new game status, which is our loop control variable. We will assign that to the game status variable we've declared. And then we're going to print that result. We're going to print the result to that game status. Okay, so let's take a look at how that first round method might look. And actually, let's actually start building this out. So the first thing I'm going to do is let's implement each of these piece by piece so that by the time we're done, we can actually see what this looks like. So, what do we have? Okay, so here we have this top statement, we have the name. Did it already? Wait a second. Yeah, didn't create it. Okay, perfect. We'll change from top statement to description. Okay, and there we go. Perfect. And now here, let's go to our main method. Now, the nice thing about by stubbing out our implementation, we can go through each step of the way and we can test. Let's see if we have everything we need. So here, status first round, we don't have a return type, is what it is. So we'll wait. We need to have some return there. Let's see if it lets me do return. No, does it let me do that? So what I'm doing here is I'm doing what's called stubbing out the implementation. If I claim I have to return something, Java won't let me even create an empty method that doesn't let me return at least something. So here, I'm just going to return, I'm going to see if it lets me return null values since status is a reference type. So it allows me to, at least compile. So here at this stage, I can make sure that the code I have, even though I can't execute it to do anything yet, at least compiles. Remember, that's an important step. Always be compiling to see if there's any syntactical errors. And sometimes it's worth stubbing out your implementation for the purposes of testing. And then the next thing we're going to do is we're going to go and take our main method here. And we're going to put our main method in here. Now, is there any questions related to this main method? Does everyone, so we already stepped through it. Does anyone have any questions about it? Or is it good? Because we stubbed out all these methods, even though I'm doing these method calls and these methods don't technically do anything yet, notice I can still compile my code. It's still valid Java code now. So I've done the one-to-one translation of pseudocode into Java code and it compiles. Now, I still can't run it yet because I really need to implement the behaviors of these other methods. Let's take a look at the behavior for first round. So we already claimed that first round is going to return a status. So what we're going to do is we're going to create a local variable that's going to be called game status. Then I'm going to rely on my dice utility class to roll 2d6 for me, and I'm going to get that sum. Then I'm going to check if the sum is 7 or yo, then I will set that game status local variable to be the win value from that enum type. If it is snake eyes or 3 or boxcar, then I will set that local variable game status to be lose. And if it's not the win, and if it's not the lose, if it's not any of those numbers, if it's anything else, then I'm going to set the game status to be continue. I'm going to take whatever the die sum is and set that as my player point. And now remember, this is a class variable. So when I set that, I will now have access to it from other methods inside this class. And then I will print out the player point. And then when I'm done, game status is guaranteed to have a value of either win, lose, or continue. So then I will return that. Does anyone have any questions about this particular implementation? So, like I said, one of the powerful things about multi-selection statements is they can be expressed either as a collection of nested if-else statements. This is using the if-else-if metaphor. You can also use a switch statement. If I wanted to represent that logic with a switch statement, I could do as such. And I'm actually interested to get your opinion on which you prefer. And I'll use either of them based off the feedback from the class. So this is the same method, but instead of using if-else, this is the alternative switch structure. Let's look at what changes here. So here, I'm going to get a dice sum from my dice utility class where I tell it to roll 2d6. I'm going to create a local variable called game status. But one of the cool things a switch statement can do that a nested if-else cannot do is it can return back a value. It can resolve into a value based off of what happens inside of the switch block. So we can pass in, which means I can do an assignment operation on it. So I'm going to assign whatever the value that is resolved from the switch statement. I'm going to pass it in the die sum. And on the case of 7 or yo, I can use a comma separated list. Then I use the arrow operator to return back a win status. And since there's only one instruction there, I don't have to use curly braces. I only need to use curly braces to create what's called a code block if there's more than one instruction, there's more than one statement, if you have that you're trying to combine together. Okay, on the case of snake eyes, tray, or boxcar, so I can separate that with a comma separated list, I'm going to return back the value status lose. And then on the default value, which means if it's not the other two cases, then this requires multiple lines of code. So I'm going to use curly braces to create a code block. I'm going to do the following. I'm going to set the player point, remember that's a class variable, to dice sum. I'm going to print out the value, hey, the point is, and then whatever is the die sum. And then finally, I'm going to use the yield keyword to yield back to this assignment expression the value of continue. So that's the one trick about using a switch statement to return a value inside of a code block. If it's a singular value, it's implicitly given the yield keyword to give back a value. Yield means it's returning back a value. If it's a singular value, the yield is implicit, so we don't have to add it. But the moment that there's more than one set of statements inside of a code block associated to a switch, we have to state which one we want to give back. And that's what yield means. Okay, so this will give back the continue, and then we can return our game status here. So is there any questions about either of these implementations? So if you don't win or lose, then you go to the next round. So remember, in our main method here in our main method, we have this while condition. While the game statuses continue, we invoke another round. Then we stop playing the game and we report that you won the game or you lost the game. So the moment you win or lose, the game is over. But until you win or lose, we are in a continue state. So with that said, let's take a look at our next round. And our next round is pretty simple, right? This is the one-to-one correspondence behind it. Here, we're going to create and return back a new game status after each round. So I'm going to create a local variable to represent what the status is for this round. We're assuming if we're playing this round that our statuses continue. Then we're going to roll 2d6 for this round. If the die sum is the player point, then we'll set this local variable of game status to be win. Otherwise, else if the die sum is equal to 7, then we'll set the local variable of game status to lose. We only set it to win or lose on the condition of my point being rolled or 7 being rolled. We've already defined that it's initialized at continue. So whatever gets processed between those two selection statements is then going to be returned back as our game status. And again, yeah, let's go ahead and take this and implement this as, we'll replace that here and we'll make sure that our indentation is correct. And then the last thing we're going to do is we're going to look at just the method print results. Now, print results requires a game status to get passed to it. And if the game status is a win, we will print that win message, you won. If the game status is lose, we'll print a loss message, which says you lose. And if it's not win, if it's not lose, if it's a continue, then we're going to print that you go on to a next round. So notice we're just taking our pseudocode and we're just mapping it. And with each implementation, each addition, I'm checking to make sure my code compiles before I add more code. The moment it doesn't compile, I debug. So notice the nice thing about these concepts is it allows me to actually kind of do some testing before I'm done the entire project. And then finally, I'm going to add in that print results, the implementation for that. So presumably now I should be able to compile my code and then I should be able to run the game of craps. And let's see if it implements correctly. So playing it now, I got a 4. 4 is neither a win or lose condition. So my point is 4 and I move to a next round. I roll an 11, which is neither a 7 or my point. So I move to a next round. I roll an 8, which is neither a 7 or my point. So I move to a next round. I roll a 4, which means I won. Which rolling a 4, that's the likelihood of me rolling that's not very high, right? Okay, let's play it again. And so this is a stochastic process, right? Because the game changes each time we run it. So I roll an 11 on the first time, so I won. I never had to go to a next round there. And here I won again. And here I'm going to lose. And I'm going to lose because I'm going to roll a 6. It's neither a win or lose condition. So I'll have to remember that. I move to the next round. And then I go ahead and I roll a 7 or a 4 on the round after that, which is neither a win or lose condition. So I go into another round where I roll a 7, which is the lose condition. And so I lose. And you could see I can keep running this game each time, and it's going to implement the game the way we expect. Here I rolled a 12, so I never progress to another round. I lose in the first round. So I think this represents exactly the rules we declared that represent our game of craps. So I think we were able to model out a relatively sophisticated build of a craps game. Does anyone have any questions?